Lesson 3.4, pre-calculus. Today we went over how to set up some application problems for exponential functions from lesson 3.1. So in lesson 3.1 you learned how to build equations, or actually write equations from given information and solve. In lesson 3.4, or actually if I gave you values of time you could plug them in. Lesson 3.4 we learned how to solve exponential equations. So today in class we put the two together. You had to build the equation and then solve the equation, not just plug in values of time for guess and check. There is a couple problems in your practice though where
Just a reminder to.
So in this case you're not given the rate. So for most of these equations in 3.1 you were given all the information. You were given the initial amount, whether it was compounded, how it was compounded, what the rate of growth or decay was, and you just had to write the equation and then solve. I'd give you a certain unit of time, you'd plug it in and you would solve or evaluate it. Now we're actually going to be solving for the final amount. We did this in class today in 3.4, where instead of having a of t equals the initial amount times 1 plus r to the t, you knew the initial amount, you knew the rate, you knew the final amount, you were solving for t, the exponent. So that was all done yet today in 3.4. Some of the people in third hour asked me questions about this, and in fourth hour some people asked, and we actually did this as a class, and we said a lot of people started finding slope of this line if it were a line, but remember that this is exponential growth or decay. Population models are almost always exponential functions, either growth because the population is increasing, or decay when the population is decreasing. So I thought we'd give you this fictional example so that you can do problems like the first two on the 3.4 applications practice, because if you don't know the rate, you can't set up the equation to solve the problem. So let's take a look. We have this example where in 1980 the population of magical fictional unicorns was 3,580, and by 2018 that population was only 1,010, which means that we have a rate of decay. So we are going to build a decay model, but we have to calculate the rate first. So I'm going to set this up that in 2018, so this is the final amount, doesn't say it was compounded daily or compounded continuously or anything like that. It just has a rate per year, an annual rate that we're trying to calculate. So we have 10,010 unicorns. The initial amount of unicorns was 3,580. And we are going to have decay here. So we have to do this equals this times 1 minus whatever the rate is to the time. Well, 2017 to 1980, that amount of time is 38 years. So started with this population. We don't know what the rate is, but after 38 years, this is the population. We're going to use this to solve for r. So my first step is going to be to divide by 3580. I'm not actually going to do that because I don't want to write the decimal value. I could reduce the fraction, but I'm just going to leave it like that. If this were, now this is where it's different, right? This is, the exponent is not the variable. If it were, we'd have to undo the equation using a logarithm. The exponent is a number, and the variable we're solving for is here. So if this were 1 minus r quantity squared, we would take the square root to undo the squaring. Similarly, we're going to do the 38th root. So 1 over 38, just like square root is 1/2, an exponent of 1/2. In other words, if I raise this to the 1/38, 38 times 1/38 is 1. So I'm left with 1 minus r to the first power. Whatever I do to the right side, I have to do to the left side also. And because it's an even root, it should have a plus or minus, but we're going to worry about that later. We'll have a discussion about it later. Some of you new in class, that for this one we want the positive because we're just trying to find the rate right now. So we have 1010 over 3580 to the 1/38th, and I have 1 minus r. So then after I do that, I'm going to have to subtract 1. So let me find out what that is first. 1010 divided by 3580, all raised to the 1. Whoops, that's not right. All raised to the 1/38th power. So right now that's what I'm looking at. But I'm supposed to subtract 1 from it because I need to subtract 1 from both sides. So now I have this decimal approximation of negative 0.03275. That would be 3.275. I better do one more. 0.3, so that's, okay. That's equal to the opposite of our rate, which means our rate is roughly, if I divide both sides by negative 1, 0.032, if I have 3%, yeah, 2752, which is 3.2752%. But this is our rate of decay, because we know that the unicorn population is decaying. So what does this mean when we've calculated this rate? You're going, well, it's positive. Well, it seems a little weird for it to be positive, but we know that it's a rate of decay. Let's look at what happens when we plug it back into our formula. Our formula for the unicorns is what we have written right up here. A of t equals a to the initial amount minus 1 minus the rate to the t. So for us, we have a of t equals the initial amount. If you look at the initial amount of unicorns being at from 1980, then you will put down the 3580, this is probably the best way, to the 1 minus 0.032752 to the t. So there's our model. If I actually, so now, right, our rate is this, but it's decay, so we have a minus instead of a plus. So now I've got 3580. Let me do 1 minus 0.032752. This gives us in the parentheses 0.967248, or roughly 97% of the unicorns remained every year. So 1981 was 97% of the unicorns, or actually just under 97% of the unicorns from the previous year, and so on and so forth. So this is what we have. This is based on t sub 0 being 1980. If you chose instead to do this equation and use, from our information, use the 1010 unicorns from 2018, then your initial time of starting would be 2018. And we'd have to be a little careful with that. But with this, I'm now going to say, hey, you can tell me, hey, what's going to happen in 2022? How many unicorns would there be? Well, I'd say 2022 minus 1980 is how many years, and plug that in for t, and I could tell you, based on this model, using the data we were given, how many unicorns there would be. Or you could say, hey, when will the unicorns become extinct? So you'd want to find out, when is there going to be one unicorn left? And then any time after that, right, the next year, that unicorn will be gone if this model continued. So you could solve this equation for t by dividing by 3580 and using a logarithm of this base. So that this solving goes back to what we did today with the application problems. But those first couple of problems in your worksheet, you have to set up a model. You have to start by setting up a model and figuring out how many years apart it is, plugging in the initial amount and the final amount, and actually calculating the rate so that you can build your equation to solve problems. This concludes the example for how to calculate the rate when it is an exponential function, not a linear function. If it were a linear function, we would do y minus y over x minus x. But we have an exponential function, so we have to follow an exponential model. Hopefully this helps clarify and set you on your way to do those first two problems in the application practice. If not, see me Monday and we'll make sure that we clarify anything you're still confused on. Have a great weekend.